I will briefly mention my journey from my hometown in India all the way up to Cardiff. That will give some sort of idea about where I started and where I am currently. Then I will move into the scientific aspect, which is mostly I'm going to talk about metal support interaction and how they play a crucial role in determining the catalytic activity. That's the key part of this presentation. So in that aspect, I will talk about what are the different kinds of metal support interaction, and specifically I will talk about strong metal support interaction, which is technically called as sometimes SMSI, and how we can tune this SMSI, and by tuning this SMSI, how we can tune the catalytic properties of supported metal catalysts. To start with, I grew up in a very small town of 500,000 people in the southern end of India. So I will have, yeah. So this is Indian Ocean here, and this is the southern end of India. So I grew up 60 kilometers from the southern end of India. And this town is the foothills of Western Ghats, which is a beautiful place in the southern part of India. And every town in the southern part of India has a characteristic or a specific temple, and each temple has its own pet animal. Unlike in Europe, pet animals in India are quite big. For example, an elephant. So typically all South Indian temples have an elephant. So yeah, that's how it is. And after finishing my undergraduate in my hometown, I moved to a relatively bigger city called Madurai. It has 2 million people. So there I did my MSc, and after finishing my MSc in India, they have a system called Junior Research Fellowship. Every student can write an examination conducted by the central government of India. If you clear that examination, you get a fellowship on your own. Then you can choose your own topic of research, your own institute, and your own supervisor. So it's a student-specific fellowship. So I got that fellowship, and I moved to the mid-western part of India called Pune, and I did my PhD in one of the best institutes in India for chemistry research. It's National Chemical Laboratory. That's where I did my PhD. And after finishing my PhD, I came to Cardiff as a postdoctoral research associate. And then I moved to Netherlands for a couple of years. I worked in the group of Professor Bert Eckhuizen as a Marie Curie research fellow. Then I got my university research fellowship, and then I moved back to Cardiff to start my independent research career. So this is the brief introduction about my journey from the southern end of India to Cardiff. So now, the three major pillars that support my career, I would say, are mentors. Dr. Manikandan, he was my PhD thesis supervisor. Currently, he works for an industry in the US. And Professor G. Sankar from UCL. Although he has the same name, we are not related. We are from the same part of India, but we are not related. So he hosted me for a few months as a part of British Council-sponsored UK-India research collaboration. Because of that, I got a position at the Cardiff Catalysis Institute with Professor Graham Hutchings as a postdoctoral research associate. Then I worked as a Marie Curie research fellow in Utrecht University. Then I came back to Cardiff to start my independent group. So these people played a major role in my transformation from a master student to an academic researcher. I would like to highlight the role of Professor Hutchings because that tenure from 2007 to 2011 played a major role in turning my career towards an academic position. So mentors play a key role in determining the career of any individual, not least funders. So I was lucky enough to get independent research funding for a fellowship for my PhD, and I got this British Council funding so that I could visit Professor Sankar from UCL, and that led me to coming to Cardiff. And after my postdoctoral research at Cardiff, I got a Marie Curie Research Fellowship, which helped me to move to the Netherlands. Because of that independent fellowship, I got university research fellowship at Cardiff University to start my independent research group. So these, in addition to this funding, institutions play a major role as well. They provided all support necessary to perform my research. So now let's talk about catalysis. So I'm going to specifically talk about supported metal catalysts. So what is the role of support? In the previous slide, I mentioned three components of the support I had for my career. So in catalysis, especially supported metal catalysts, support play a major role in determining the catalytic activity of the material. Typically, supports are used to disperse metal nanoparticles, to hold them, increase the stability. So most of the times, we think that it is an inert material. However, support play much more than that role. So the types of metal support interactions are charge transfer. For example, there can be a charge transfer between metal and support that determines, the oxidation state of the metal as well as the metal ion on the support material. So the Fermi level difference between the metal nanoparticle as well as the support determines the extent by which this kind of charge transfer takes place and the direction of this charge transfer. So that can take place between metal nanoparticle and the support. Another important interaction is interfacial perimeter. So the perimeter, the interfacial atoms between the support and the nanoparticle, they play a crucial role in catalysis. For example, in CO oxidation, they play a major role. And in the next couple of slides, I will show you how we can manipulate this interfacial perimeter sites to tune the selectivity of a catalyst. So these perimeter sites play a major role in the metal support interactions. In some cases, this support material can influence the structure of the nanoparticle itself. And in turn, they can affect the catalytic activity. So that is also possible. Another example or the other kind of interaction, it is the components from the support, they can interact with the metal nanoparticle during the heat treatment or during the catalyst synthesis or even during the reaction. They interact and they form sort of an intermetallic compound, or the composition of the metal nanoparticle changes because of the components of the support. So that's another kind of interaction between metal and support. And one relatively well-known phenomena is the strong metal support interaction, which is called A-SMSI. And I will talk briefly about this particular A-SMSI during the later part of this talk. So to start with, I will give you an example how by tuning the interfacial site, metal support interfacial sites, we can tune the selectivity of a particular reaction. For this, I'm going to take an example of a simple benzyl alcohol oxidation. So the catalyst used here is supported gold palladium nanoparticles. So we use oxygen as the oxidant, solvent-free benzyl alcohol. So here the targeted compound is, or the compound of interest is, product of interest is benzaldehyde. However, we get large amount of toluene in this reaction. Now, we found that the origin of toluene is by a disproportionation reaction, very similar to our Cannizzaro reaction. So 2 moles of benzaldehyde disproportionate to benzyl alcohol, 2 moles of benzyl alcohol disproportionate to give toluene and benzaldehyde in equimolar mixture. This reaction is responsible for the production of toluene, whereas oxidative dehydrogenation of benzyl alcohol results in benzaldehyde, which oxidizes to form benzoic acid. So there are two parallel reactions that happen in this particular in this flask, for example. So now we don't want toluene, or in other, if we don't want toluene, we should somehow suppress this disproportionation reaction. We used I will come back to the logic behind choosing different support in the next couple of slides, but we prepared different gold palladium catalysts with different supports. For example, titanium, niobium oxide, carbon, magnesium oxide, and zinc oxide. If you look at the first three catalysts, we have 25, around approximately 25 to 30% of toluene is formed for the first three catalysts. For the last two catalysts, we have almost switched off toluene production. However, the conversion is much less. The time online plot for all these catalysts are given here. Carbon is the most active, and zinc oxide is the least active. Magnesium oxide is the least active catalyst. Now, from the stoichiometry of these two reactions, we can easily separate these two reactions more or less quantitatively. So this is the reaction for the production of toluene. So 2 moles of benzyl alcohol give 1 mole of toluene, 1 mole of benzaldehyde, and 1 mole of water. Now, from the amount of toluene, we can calculate how much benzyl alcohol is consumed for this particular reaction. Now, from the amount of total benzaldehyde, if we can subtract the amount of toluene, we can calculate the amount of benzaldehyde produced exclusively by oxidation reaction. So based on these simple calculation, we can calculate the turnover number for disproportionation reaction and the turnover number for oxidation reactions, although this happens in the same pot. Okay, so we cannot these two reactions happen simultaneously in the same pot, but based on the stoichiometry, we can separate these two reactions more or less quantitatively. And if we plot for all the 5 catalysts, the oxidation reaction is almost the same. The turnover number for the oxidation reaction is almost the same. But for the disproportionation reaction, you can see there is no disproportionation for zinc oxide and magnesium oxide, and carbon supported catalysts catalyze these reactions very effectively. Now, if we look back, the most active catalyst is not because of, very active for oxidation reaction. It is because of an additional unwanted reaction happening at the metal support interface. So how we come to know that? If we change the support, we can see a change in the activity for disproportionation reaction. That shows that the metal support interface is the active site for this particular disproportionation reaction. Whereas this, even by changing the support, we don't see much change in the activity for oxidation reaction. So kind of we can conclude that the metallic sites are responsible for the oxidation reactions, whereas the metal support interfacial site is responsible for the disproportionation reaction. When we know the active site is the metal support interface, we can tune that active site by changing the support. By changing the support, we are changing the metal support interface, and that changes the activity for this disproportionation reaction. And consequently, we can tune the selectivity for this reaction. So this is an example where, by tuning the metal support interfacial site, we can tune the selectivity of a reaction. And another parallel concept is for production of benzaldehyde, this kind of adsorbed species is needed. Okay, so for getting this kind of alkoxy species, a basic support is necessary. When you have a basic support, it deprotonates the alcohol to form this alkoxide species that adsorbs on the palladium site, and you can have the oxidative dehydrogenation reaction. So that's the rationale behind choosing basic supports for this particular reaction. Now, when we have a basic support that is active, that can act as a base, and you have a metal that can act as a dehydrogenating metallic site. So what we did, we combined these two activities. So we combined the dehydrogenating activity of gold palladium and the basic feature of magnesium oxide, and we performed a cascade reaction. We took benzyl alcohol and we dehydrogenated to form benzaldehyde, and we used acetone as the solvent or a ketone as the solvent. So you can have base catalyzed aldol condensation. And once you have that aldol condensation, the hydrogen from this dehydrogenation reaction is used to hydrogenate this double bond. So what we have done is we have done a series of reaction by exploiting the basic feature of this support, as well as the dehydrogenating ability of this metallic site. Now, let's go to the next aspect of SMSI, or the metal support interaction, which is sometimes called a strong metal support interaction. There are a number of classes of this SMSI. This classical SMSI is very well known, reported by Tauster et al. Sometime in the late 70s. They reported that when you have a metal nanoparticle of platinum group metals, and when you have a support that can have variable oxidation state, what happens is when you heat this, when you reduce this catalyst at very high temperature, the support material forms a layer of this support oxide on the metal nanoparticle, and it completely covers that. So that is the classical SMSI. It's pretty much well known. But there are a few other kinds of SMSI, which is adsorbate induced SMSI, reactive SMSI, oxygen induced SMSI. These are relatively less known in the literature, and active research is being carried out recently on these kind of strong metal support interactions. What are the features of this SMSI? The charge transfer between metal nanoparticle and the support, and mass transfer between support and to the metal, because of the mass transport, it covers oxide layer covers the metal nanoparticle. Because of this, catalyst can have improved stability and sometimes can have better performance. Okay. Now, this is classical SMSI. So when you have a reducible metal oxide and you have a metal, when you hydrogenate this catalyst, say around 500 or sometimes less, slightly less than 500, what you get is a support layer on the metal nanoparticles. So this is called classical strong metal support interaction. The characteristic features of this SMSI is suppression of small molecule adsorption. For example, because the metallic sites are completely covered by a layer of this metal oxide, these metallic sites are not accessible for small molecules to adsorb. For example, hydrogen chemisorption or CO chemisorption. You can see a substantial reduction in the CO chemisorption level when these metal particles are covered by the metal oxides. I will show you an example in the next slide. And another important feature is when you calcine this catalyst or oxidize this catalyst, back you get this metal exposed. So this phenomenon is reversible, completely reversible by oxidation. You can see here, this is an example reported by Tao Zhang group from Dalian. Say, this is a platinum on titania. This is CO drift spectroscopy. This peak corresponds to CO adsorbed on platinum nanoparticle. You can see a huge intensity of this CO. Now, when you reduce the catalyst at 250 degrees C, you can see a substantial reduction in the peak area of CO adsorbed on the platinum surface. Or in other words, the platinum is not available for adsorption. When you heat it under 500, you can still see a very substantial reduction in the CO adsorbed on the platinum surface. The same catalyst reduced at 600, absolutely no platinum exposed. Or in other words, the platinum is completely covered by titania overlayer. Okay, but when you take this catalyst and oxidize it at 300 degrees C, you can get the peak back. Or in other words, the platinum site is exposed. So this process is what is a typical characteristic feature of SMSI, strong metal support interaction. And platinum is a platinum group metal that can dissociate hydrogen. Titanium oxide, here it's a reducible metal oxide. Now, recently, very interesting reports came in the literature. Instead of, here, these things happen because of high temperature hydrogenation. One group from Taiwan reported the reverse of this for gold on zinc oxide. For gold on zinc oxide, when you oxidize the sample, the gold surface is covered by zinc oxide layer, monolayer. This happens when you oxidize the sample. For example, here it's the fresh catalyst. This is the CO adsorbed. You can see CO adsorbed peak. When you oxidize this sample, you can see there is more or less no adsorption of CO on the gold site. But when you hydrogenate this oxidized sample, you get your CO adsorption back. So this is what is called as oxygen-induced SMSI or O-SMSI. To the best of my knowledge, these two are the two reports that report this oxygen-based, oxygen-induced strong metal support interaction. Very recently, a group from Christopher et al., they reported something called Adsorbate-induced SMSI. So this is for CO2 hydrogenation over rhodium, supported rhodium catalyst. So they were hydrogenating carbon dioxide, and the objective was to get as much carbon monoxide as possible rather than methane. Okay, so what they did, they hydrogenated the catalyst, or they treated with hydrogen. What they got was a typical SMSI for titania as well as niobium oxide, because they are reducible oxides. And this overlayer is impermeable. So what they got was mostly methane. You can see this is methane selectivity, and this is carbon monoxide selectivity. The fresh catalyst they took, and they used carbon dioxide, a mixture of carbon dioxide and hydrogen, and they treated the catalyst, and they formed a permeable monolayer of this metal oxide. So that's what they called it. They call it as adsorbed induced SMSI. So this permeable monolayer is porous. So the small molecules can enter into this and they can access the metal nanoparticle. Consequently, what they got was more or less exclusively the CO selectivity. The selectivity for CO is much higher because of this, adsorbed induced SMSI. So this is another kind of strong metal support interaction. So what we did, we contributed in this field a couple of years ago. So for this, we used nitrostyrene hydrogenation, chemoselective hydrogenation of nitrostyrene. And when we use platinum catalyst, it selectively reduces the nitro group, and it doesn't reduce the carbon-carbon double bond. So this is the pathway it goes. So we used platinum on titania as the catalyst. We prepared this catalyst by impregnation method. What we did, we prepared different loading platinum on titania catalyst. And one batch, we reduced the catalyst at 450 degrees C, and another batch, we calcined the catalyst at 450, and then we reduced it. For 0.05 loading, the reduced only catalyst is much, much more active compared to the calcined plus reduced catalyst. On the other extreme, if you increase the loading tenfold, 0.5 loading, the calcined plus reduced sample is much, much more active compared to the reduced only catalyst. And we know for sure higher loading means A-SMSI is predominant. A-SMSI is predominant. That's why when we calcine and then reduce, we can reduce the A-SMSI. Hence, platinum sites are accessible for catalytic reaction. So in other words, what we have done is we have reported a size-dependent A-SMSI. So for very small particles, we need a much, much, much higher temperature to cover the platinum nanoparticles. Whereas for large particles, we need a much lower temperature to cover the platinum nanoparticles. And we have certain loading or certain particle size where it's more or less the same. So this shows, size-dependent A-SMSI, which is not very well known at that time. It's the A-SMSI is dependent on size. As you can see, the best technique to study A-SMSI is CO chemisorption or CO drifts. As you can see, the reduced only catalyst, or let's start here. The calcined plus reduced catalyst absorbs lots of CO. This is for 0.05 loading. For reduced only, it still absorbs some amount of CO. If you take the other extreme, the reduced only catalyst, the intensity is much, much, much lower compared to, say, calcined plus reduced. That shows here, in this case, the platinum nanoparticle is more or less completely covered, whereas for 0.05 loading, for the same sort of heat treatment, still platinum sites are exposed. And what we did, we tried to correlate peripheral sites with total surface platinum exposed sites. So we tried to correlate the reactivity or initial rate with the total surface platinum exposed surface. We didn't get a much acceptable correlation. Whereas when we correlated the peripheral sites versus the rate of the reaction, we had a slightly better correlation. That shows that, the peripheral sites, the platinum titanium oxide peripheral site, these are responsible for the better activity of this reaction. And after that, a couple of groups started reporting this size-dependent A-SMSI in gold on titania, for example, Du et al. I think they are from Dalian Institute. They reported, as you can see, for 3 nanometer, even after reducing the catalyst under 400, still they could see some level of CO absorption. Whereas for a 13 nanometer and 13 nanometer gold particle, 400 is completely gone. I mean, there is no absorption of CO at this stage. So they say that, they more or less observed what we observed for the platinum on titania situation. Now, to sum up, metal support interfacial sites catalyze the disproportionation. By tuning that interfacial site, we can tune the selectivity of this reaction. And I gave an example about size-dependent A-SMSI, and by tuning the thermal treatment procedures, we can tune this A-SMSI, and support is crucial for career as well as in catalysis. And I would like to thank Alexandra Bonds, Lifang, and Meg for doing this platinum on titania work, and my colleagues and collaborators, Graham Hutchings, Andy Bale for X-ray absorption spectroscopy, Chris Kiley, Xianhe Sultan for the fantastic microscopy. And thank you all for listening.
Thank you, Sankar, for a really fascinating talk and a globally diverse career. We've got a question in the Q&A from Sudhir, who's asking about the reason that the peripheral PT showed more activity. Could you elaborate a little, please?
I'm sorry, I think I'm not understanding the question. So the peripheral platinum site is the site that is responsible for, say, for example, I'll try to. So this side, if this is platinum and if this is titania, this side is responsible for, is the active site for this particular reaction. This is where the adsorption takes place, and maybe the platinum site is responsible for the dissociation of hydrogen, and the adsorption of this nitro group happens at the interfacial sites because we need to adsorb. There are two functional groups in this molecule, a carbon-carbon double bond as well as nitro group. And we want to adsorb only this nitro group to get chemoselectivity. So when you want such a high level of chemoselectivity, we want this to adsorb at a specific place. So we think that the metal support interfacial site is responsible for the adsorption of nitro group, and that's why that is we get a good correlation between the peripheral sites as well as for the reaction rate. Have I answered the question?
Sudhir, did that answer your question?
Okay.
Yes, perfect. Thank you. I have a question that goes back to sort of your career path. Obviously, you've moved around a lot.
Yep.
For someone who's just starting out in sort of postdocing effectively, do you have any advice for them in choosing one location or one position over another when they're looking for where to go?
The best advice would be go to a place where you won't feel comfortable, not in the same country where you have lived, because that gives you a very interesting experience, or you get exposed to totally different research culture as well as living culture that shapes your career substantially. That was one of the best decisions I have ever made, moving from India to UK and then to the Netherlands. This gave me a very interesting, perspective about research, how we approach a problem. Different countries approach it in slightly different way.
Okay, thank you.
And very important, try to get your own fellowship. That's crucial.
Yeah, it's easy to get stuck postdocing in some ways, isn't it? And just keep going.
Yeah.
Sudhir is asking if there's any other studies for papers that you would suggest for the oxygen-driven MSI.
Any other studies for? To the best of my knowledge, I have only two systems I have read. One is gold on zinc oxide and gold on hydroxyapatite. So these two systems exhibit this oxygen-induced A-SMSI, which is quite the reverse of typically what we see, hydrogen-induced A-SMSI. So it's an interesting phenomena.
Very fascinating. It's always difficult to get new things when you've got something that's so new. Yeah.
So still, we lack of understanding. What drives this oxygen-induced A-SMSI? A fundamental question: what drives this? That's a good problem to focus on.
I think Sarayuti has a question. Sarayuti, do you want to ask your question?
I don't know how to type that into the Q&A box, but it doesn't.
Unfortunately, panelists don't have access to the Q&A box. It's one of
right. Okay. I just got the question about that disproportional reaction of that toluene formation.
Yeah.
When you do that, this is very interesting indeed. When you change the support and it creates different selectivities of those products, you use 1% gold and palladium, but if you change is that optimized the content of the gold and palladium?
Yeah. So I'm not going into the other side because we can always optimize the metal. Okay, metal and the composition of these two metals, the structure of these two metals, that can have a strong influence on the product selectivity
as well. Yes.
But we deliberately we kept the composition the same. We prepared using a colloidal method. Because of that, all the nanoparticles are of the same size. So we kept everything the same. From the metallic side, everything is the same.
Right. Yeah. Okay, that's very good. I have been working with this type of things as well, with the encapsulated, the interaction with the supports and all that, because it's influenced so much on the activity and selectivity of some of our reactions. So that's very good talk. Thank you.
Yeah, I mean, there is another report from one Chinese group. I don't remember the name. What they did, they have covered this metal nanoparticle with encapsulation, and then post encapsulation, they started making holes around this covering to make it porous, and they call it as a reverse, A-SMSI. So this strong metal support interaction has gained lots of interest in the last couple of years.
Yeah, agree. Yeah.
So Studio has a follow-up question where he asks, or they ask, do you see oxygen-rich support like cerium dioxide would be better for such reactions?
I cannot say. It's a very general question. Okay, for some reactions, ceria can exhibit strong metal support interaction because it's a reducible oxide. Korma has reported some sort of SMSI, the advantage of having this SMSI for chemoselectivity. So for some reactions, they have some advantage. For some reactions, no, they do not have any advantage whatsoever. And in some reactions, they are detrimental because it covers the metal nanoparticle. So it all depends on the reaction.
Okay, thank you very much. If there's no more questions, we will just take a moment's pause and start with Dr. Rachel Cowan at past in case people are joining specific talks. Thank you very much for such an excellent talk. As you can see by the diversity of questions, everyone's very interested. So thank you very much, Sankar, for that. I will stop the recording now.